Okay. Hello, guys, everyone in the FORCE 2020 Zoom meeting of September. Today is the birthday of our mentor and the man who invented FORCE, Chuck Moore. So a great huge to Chuck. We wish him well and to enjoy the birthday with his family and friends.
Happy birthday, Charles Moore. Yeah.
Happy birthday to Chuck.
Yeah.
And then we have in the meeting, let me see, I share with you my screen with the different presentations. We start today with Jason. Jason, are you there?
Yes, I am.
Okay, so go ahead with porting ESP32 FORCE to the LilyGo T deck.
Okay, here we go. Share screen. Okay. There. Okay, before we get started, I'll just make it clear that obviously the bulk of the coding that happens in this case of porting ESP32 FORCE to a new piece of hardware, which is what this is going to be about, involves a lot of C, C++ through the Arduino IDE, and there's obviously some FORCE as well. But the key objective here is, we want to get ESP32 FORCE onto as many different devices as we can. And in this case, the idea is to fulfill the need for some sort of portable FORCE device. And I presume that there may be some who will point out to me that you can actually install GForce on your mobile phone, and I am aware of that. I've had GForce on my phone on occasion. However, I think some of you will agree that the allure of having a FORCE specific device is just something that's too attractive to ignore. So this is what that's all about. You may have seen some of my previous efforts. I'll just switch the camera now. If you are seeing, okay, right. All right, I see that. Seems like that becomes a little bit more difficult once you're sharing. Okay, well, anyway, we'll just start straight away, and then we'll leave that for a demonstration for later. So this is all about, the ESP32 FORCE source code obviously is built to be delivered through the Arduino IDE. And so as a result of that, a lot of this work is about preparing the ESP32 FORCE code to run on your particular instance of ESP32 chip. Now, the specific piece of hardware that I'm targeting today, I got very excited about it when it was announced, and that's specifically the LilyGo T-Deck. If you think it looks a lot like a BlackBerry, it's because it really does look a lot like a BlackBerry. It has the same keyboard. It literally has a BlackBerry Q10 keyboard. I'm not sure who's making it. Presumably whoever was subcontracted to make it for BlackBerry just figured, I'll just continue and see what happens. And you have the same, you in fact have the same rollerball as well that can be pressed down in the middle to make a selection. And it basically comes as a bare naked circuit board. So, but they do provide a 3D printable casing. We'll just quickly go through what makes up the device. You can see the front and back and all the different views there. It runs on an ESP32S3, which means it's quite powerful. It has a few more pins than your regular ESP32. It has 8 megabytes of PS RAM. It has a touch screen. It has the trackball. You have a LoRa option. I bought the one without LoRa. You have micro SD cards, microphone, dual microphones actually, speaker, and you have ready-made is ready to go with a battery connector. What sort of size of battery can you get into this thing? I'm not 100% sure at the moment, but it looks like it might be about an 800 milliamp hour or 1000 milliamp hour. Eventually I'll find out when I try it. Now next, this is a comparison of the T-Deck with the M5 stack. Now previously I did pretty much the same thing to transfer ESP32 and get it running on the M5 stack. Clearly we can see here the screen is much larger. The M5 stack didn't have a touch screen. It also used a regular ESP32, so you don't have the benefit of PSRAM there. So the addition of PSRAM obviously brings thoughts of graphics and things like that to mind, you know, which I shall be exploring in the near future. It's obviously, because it's a bare circuit board, it's not really turnkey like the M5 stack. The M5 stack comes in a quite neat, ready-to-go, self-contained device with built-in battery charger, and comes with a docking station and everything. However, even so, the T-Deck is actually cheaper. So in a great sense, you're getting quite a bit more hardware for the dollar. The first shortcoming I found is that you don't have markings for all characters on the QWERTY keyboard of the T-Deck. This sort of harks back, I suppose, if you ever use a BlackBerry, you know, it's exactly the same sort of keyboard. So less than, greater than, and equals, and all that. All of those are missing, and we shall have to find some other way to address those. So, what does it take to get ESP32 running on the T-Deck? You have to head to the T-Deck GitHub page, where you can pull out the examples, and also crucially, they have collected all the driver libraries that you need to do this. So for all the devices that you have on board, in particular, in this case, we're looking at the keyboard, which is connected on I2C, and the display is on SPI. Now, you might like to note, actually, that there is more than just the ESP32S3 on the device. There's actually a C3 on board as well. The C3 is being used purely as a microcontroller to decode the keyboard and act as an I2C slave. That sounds like a bit much for a keyboard controller, but never mind. I suppose you know, well, you get more ESP32 bang for your buck. Oh, how did I get there? Sorry about that. Press the wrong key. Right. So once you've got your libraries and installed in the appropriate folders for Arduino to recognize them, then you need to configure make sure you've got, well, if you're already using ESP32 and compiling it for the Node and CU boards, then you've probably already got all the platform support files on there. But in this case, you need to make sure that you select the ESP32S3 development module. And I've provided, and there's a few things that you need to change as well, but I've provided all of these in the screenshot here as a reference. And then after that, you can just make sure that it builds successfully at this point. And the next thing to do after that, and you know, you can verify that at least it works through the serial port as it would on normal ESP32. And the next thing is I use a text buffer library. It's not necessarily the best one, but I also use this on the M5 stack. It does the job, and for some reason that is not really known to me at the moment, it works far faster on the S3 than it does on the M5 stack. I shall find out in due course. And then the next step after that is we have to start adjusting the source code of ESP32. The first thing to do is to add in the library headers. Principal among them, you need SPI, you need the TFTE SPI library. SD card is already in ESP32. You need the wire library, and The last one is the TB display, which is for the text buffer. Then after that, you have the definition for the slave address for the keyboard. I'm not sure, can you see the mouse pointer in this? Okay, all right. So then you've got the different definitions for the pins for the I2C and so on. So you get all of those in, and then make sure you define a TFT object over there, and then that basically creates a display instance.
Jason, if you switch off the selection points on top of your screen, the picture will get bigger, and we might even be able to read what you have been pointing out. Well,
okay,
perfect.
Okay. Okay, here we go. Yes, so we have the header files here, and then the slave address defined is hex 55, and then the pins. Next thing, next is you have some conditional defines that are provided to cater to the different sorts of peripherals available on the different types of ESP32 boards. I've had to change it slightly. You don't really have to, but if you want that sort of support for example, for the second serial 2, that's the only reason why I've done this here. So basically, it used to lump it all so that you wouldn't have serial 2 support on the S3 as well. But really, the only thing that's missing from the S3 in this case is the DAC. So this is why this is here. This change is actually optional, but if you want it for completeness, this is probably what you need to do. Next, we'll get ready. You need to add to the vocabulary. So in the vocabulary list for ESP32 fourth, we need to add this highlighted here, which is we just create a vocabulary set for the TDEC. In this way, we use the V macro to create a vocabulary. And then we'll start defining the functions. So these are the C-level functions to basically give us the hooks into the I2C to connect to the keyboard and to the SPI display. So the 3 key functions we need to redefine are basically characters available in the stream, to get a character, and to write the character. So character available, I've prefixed it with TD so that I know that these are only for the TDEC. You have to use your whichever system that is needed on your piece of hardware. In this case is I2C, and we'll request to find out whether there's a byte available from the slave. And then for getting a value, it's pretty much the same thing, except that we actually retrieve the byte and return it. I've simplified this since this screenshot because well, I found that it didn't really make a difference to have all this code in there. But you just basically return the wire read, and that will do. And then for writing a character, you want to write a character to the screen. In this case, as mentioned, since we're using the text buffer display, it gives us a little bit better handling of word wrap and so on. Otherwise, if you don't use some sort of text buffer, then what you'll find is that you have words being cut off, wrapped in mid-word. And this way we ensure that the whole words are wrapped to the next line and so on. And it helps us do some of the scrolling. You also find that since it redraws the whole screen character by character, it's not really that fast. One of the things I'd like to get into next would be to use the hardware scrolling feature of the screen controller, and that would give us much faster scrolling and smoother as well. And then so now that we've defined these 3 functions, we have to add our own macro here for the required TDEC support, and this essentially adds in these words into our vocabulary. Right, so we defined the TDEC vocabulary set before, and that will add the TD key question mark, and TD right into the TDEC vocabulary set, and then appropriately providing the handling for the stack as needed. So once we've done that, we have to, so if you notice, we had to create this required TD support. This is just following the existing naming convention that Brad has given it. And this shows that, you know, since it's required, it obviously, you know, otherwise your screen, your keyboard won't work. Then we add it to the platform opcode list to make sure that all our words are added into the vocabulary set. And you can find this around the 450 line region, and you'll see that we've added it in here. So this, up to this point, this gets you basically all your words added into the vocabulary set at the C level. Next, we have to do a little bit more C, and that is to initialize the screen, of course, and all the peripherals. So we have to go near the bottom and to the Arduino setup function. And in addition to the existing ESP32Forth setup, we have to add the appropriate functions to power on the board peripherals. There's actually a required delay of 500 milliseconds. But what I've done is, since we have other functions that need to occur here, I've taken advantage of that fact to get all of those things going. And this additional delay here is because it's basically required to allow all the systems on the board to start up. The main reason for it is actually to allow the ESP32C3, which is being used as the keyboard controller, to start up. Then we can connect to the I2C of the slave, the keyboard controller, and check that it exists and it's working and responding. Then we initialize the text buffer display, and we can get on with the rest of all. And finally, we get to the part where we have to put in our previously created vocabularies into the hooks that exist within ESP32Forth itself. So this is in the, so the source code of ESP32Forth actually consists of the lower level hardware C and C++ code that implements the interpreter, and then on the basic primitives. And beyond that, it also includes a fairly large piece of Forth source code included as a string that implements ESP32Forth as Forth source code. And here is where we put in the hooks. So ordinarily, when you find this piece of code in your source code, you'll find that the default type and default key and default available key words have been defined to use the serial type, serial key, and serial key available words. So this is where we replace those with the words that we created before to interface with the TDEC hardware, so that it will use the display and the TDEC hardware keyboard as the default method of entry and output. Once you've got this, you can compile the source code, and in fact, it should work. And you'll be able to type, and it should display on the screen. Where would I go from here? There is actually quite a bit of, if you look on the TDEC GitHub page, there's quite a lot of code in there about making use of LVGL. That shouldn't really come as a surprise, because there's quite a bit of LVGL work out there for the ESP32. If you've ever played with any of the other examples and like the VGA ESP32 board and so on, has lots of LVGL based implementations, and that gives us an interesting possibility, because LVGL will make it possible for us to make full use of the whole screen real estate, use that text area widget for better text handling, be able to use the touch screen have use of the trackball and so on. So that's an interesting thing where we could add a lot more graphical features into ESP32 And as I mentioned before, if we go back to the picture of the keyboard, there's actually a lot of symbols that aren't there. Right? You've got a minus and plus, we've got underscore, all typically possibly used for typing emails and text messages, but we're missing quite a lot of other characters here. So LVGL would give us an interesting possibility, for example, to create a legend overlay when you needed it, when you are trying to type some other type of symbol. We can use the Alt key over here and so on. I can't really remember how it was in the BlackBerry. That must have used a similar sort of system. But that would be something that would be worth implementing. Otherwise, you wouldn't be able to type less than or greater than or equal to begin with. And the next thing after that, of course, is to get a battery as well and test out the battery life, 3D print the enclosure. At the moment, it's a bit hairy and airy-fairy to hold it, because essentially you're always touching the circuit board on the back. So it'd be really nice to 3D print the enclosure, in fact, they do provide STL files for an enclosure for you to use. There have been a number of other users who have created a chunkier enclosure that accommodates a 2000 milliamp hour battery. Quite a lot of talk in the forums about a 2000 milliamp hour battery, so I somewhat presume that maybe an 800 milliamp hour battery isn't going to last you very long. Okay, so now we can get to the camera, and let's see now. I will switch to this. Okay, so we shall try to do a bit of a demo now. I'll just reset the board, and then you'll see how it restarts. So that's fairly good. Let's type words.
Jason, can you dim the display because it is too bright? It's not readable.
Right, I see. It's not possible to read it? No, there isn't a... we could control it programmatically, but I haven't provided a means to do that yet. We should start creating some sort of forth code that does some screen mirroring online. So you can do numbers, you have to type it through the symbol, and then we can add two numbers together and display it.
For some reason, it's not full screen on my end. Is that true with everybody else? Yeah, is there the host? Can you make it?
I can try something else. Share screen.
You should be able to click pin on the window. It should bring it up full screen.
Yeah,
so pin on speaker. Correct. Pin the speaker, right? Okay.
But that is something that you have to do on your client.
That is correct, yes.
So in other words, you have to go through this little 3-dot menu, or when you mouse over somebody's little image, at least under Windows, you get in the upper right corner, you get this little 3-button thing. If you click on it, you get a drop down. And the fourth one from the top says pin.
So I just hovered over his, I right-clicked, and there was two choices and one was pin, and I did go full screen.
Yep, that's the one.
So, well, it works exactly as you would imagine if you had a handheld BlackBerry styled ESP32
Jason, if you can make your surrounding light in the room brighter, then the camera may adapt so that we can even see the display of the LilyGo or read the display. Right now, it's all wishy-washy.
Yeah, I see what you mean. I made it. It's not actually legible.
I think it's more about resolution, right? Because even the laptop is not clearly visible.
Yeah, that's right.
Very cool.
Well, you know, it's the dream of having ESP32 in your pocket wherever you go, right? And this is why I say that you know, it's a bit nary-fairy using it like this without the enclosure, because well, over here it's tropical weather, which means that my hands are sweaty, and I'm just imagining I'm getting salt onto the.
Are you going to use this for an industrial controller for the distillery?
Oh no, this is for amusement. this is for the pure ability to say that, you know, I can pull this out and program in ESP32 wherever I go, and to try out ideas on the fly whenever I have them. That's, you know, that's part of the reason for doing it, and the reason why I don't use G4. You know, there's just enough differences here and there. I find that if I could really just use ESP32 all the time, then that's what, you know, this is what I'm trying to achieve here.
Yeah, it's really cool.
And if you look at this keypad, of course, these are all normal tactile buttons. They're horrible. They're really horrible. I mean, I've had this for ages now, and if you see, in fact, this is a lot slower. If I can, you see ESP32 booting up here. I don't know why. It is really a lot slower. It's running the same libraries.
Well, but one is a SPI interface, the other is a parallel port interface.
It seems to me like both of these are SPI, you know?
No, I think the new one is a parallel port.
Well, good for us then.
But SPI should be able to run faster than that.
Yes. Part of the latency is also due to the library. It's not really the greatest. My thoughts are either to write my own library, taking into account what facilities we do have available to us, or else try the LVGL route as well, which would be interesting, because if we wrote our own text buffer library, it wouldn't really help us make full use of the trackball over here. So it's a nice piece of hardware. This here you see is a speaker. This, I believe, is the touchscreen controller. This is the ESP32C3. This is the S3. This is micro SD card. Yes, and we
Do you have external pins? Can you talk to the SP32C3 S3?
There are some, but many of the pins are used up. Many pins are used up.
Then it's a parallel. Yes, then it's a parallel
Yeah.
interface. Yes.
You see microphone here and a microphone here as well. There are really so many devices here. And of course, some of the pins are used up for the LoRa. These pins here are actually for accessing the C3.
Really cool.
Okay, that's it. Any other questions? Using this method is typical of what you do to get it onto other devices as well.
Arfat here. May I have a question?
Sure.
So, how can you store your words, or
you have to use the block.
sorry, say again. Sorry.
You have to use the block storage.
Right.
In the SPI FFS.
Right.
Jos has a question, Christian.
Yes, thank you. How much what's the lifetime of a battery?
Yes, I would like to know that as well. But what a lot of people do is that they find a spot here, but of course, you know, you have to manage all of these things a bit carefully, right? And it typically within the casing that if you 3D print it, the battery sits across here because this speaker already came attached right in the middle, which I don't know if that is the most strategic location. It's probably the only place they could stick it other than up here. And it seems like quite a few people have redesigned the casing so that they could accommodate a 2000 milliamp hour battery. Whereas the standard casing probably only accommodates 800 milliamp hour. So there's probably some precedent for thinking that the standard an 800 milliamp hour wouldn't last very long. How long is not very long, I don't know yet. So I shall try it out and report in the group.
Magst du Kräuterfleischsalat?
Ja,
Daraus mache ich immer einen Nudelsalat. Da
ja,
nehme ich
sowas
Nudeln.
geht.
Bitte?
Ja. Aha.
Vielleicht für morgen?
Ja.
Okay. More questions to Jason and to his project. Anyone?
Yeah. So my hand up. Yeah. So Jason, yeah, you're right. It is a lot of fun doing that. And how are you going to use this in the weather station? That's what I want to see.
Yeah. For the weather station, I'd probably prefer the M5 stack instead.
Okay. All right. I'd like to see that. Thank you.
Great question. Great question. Who else? Rolf Hemmerling or Christian Hintze questions? Anyone? Frederick Segard in the meeting also. Hello, Frederick. Did you like it?
Yeah, definitely. I've been away for a while, but I'm slowly going back into it and learn. I started to learn, forgot everything, then relearning again, and I'm actually trying to do my own forth for my platform. Not sure how that's going, but it's advancing. But I'm trying to find pieces of code here and there. But I would like to have something fully functional for the Z80, but a lot of it is like you need CPM or something else. But I wanted to run.
But no questions for this for Jason. questions?
Well, I did have one earlier, but it was answered. It was about battery autonomy. So
Excellent, excellent. Who else? If not, we move on to the next participant. No more questions?
It's very cool. That's all I can say. I want one now.
Okay, let me check out.
maybe one. So how long did it take to implement everything?
Just one sitting really, and an hour. But then the thing is that I already knew what I was looking for. And I had some because I'd already done the M5 stack before, so it was sort of familiar ground.
Okay, fantastic. Thank you, Jason, very much. Another great presentation. Now, gentlemen, we move on. Our next participant is Lennart Benschop from the Netherlands, and he has implemented FORCE on the Agon single board computer. Lennart, are you ready to present?
Yes, I'm ready. Can you allow me the screen sharing enable?
Of course, we are in the commands.
Yeah. Yeah. Allow that a window, and then I'm going to the LibreOffice thing, and now I lost that one. Yeah, the LibreOffice. Yeah, I've only a short presentation. Let's see. I think I shared my screen, but I don't see it myself. Oh yeah, now I see. Do you see my presentation, the FPGA for Agon Light screen now?
Yes.
Yes. Yes.
Yeah, okay. Then let's first, well, we have a shorter presentation than the previous one. First, I'll talking a little bit what's Agon Light, then a bit of history about my involvement with FPGA and how this FPGA came about. I'm talking something about the prefix assembler. That's a feature of MyForth that I took from FPC, from Tom Zimmer. He's also in the call, I think. Is he? And then something about the internals of that FPGA. And then I'm going to show you some bits of source code, a bit and a live demo of this thing on the emulated Agon Light, not using camera, so the screen should be readable. So first, what's Agon Light? Agon Light is an 8-bit computer. Say the ultimate black belt of 8-bit computing, they say. Bernardo Kastrup designed this hardware with an EZ80. That's an extended Z80 with say an original Z80 mode inside. You can run standard Z80 programs, but you can also use in extended mode, and then the 16-bit registers become 24-bit. That has some interesting consequences if you program the thing, because not everything is as easy in the EZ80 mode. And the Agon Light, in fact, uses an EZ80 F92 part that has the EZ80 core, 120K of flash, and some built-in peripherals like timers, parallel ports, serial ports, SPI, you name it, it's in there. And The other thing is it's connected to, there is 8 kilobyte of static RAM inside that chip. If you don't use external RAM, you at least have this 8K of RAM also. And there's, but we do have 512 kilobytes of SRAM. So you get some playing room, some room to play with. It's a nice machine. Then instead of a real video hardware, we have this ESP32. It's used with the FPGA library, and it's used like a terminal. That you send bytes over the serial port to it, and you receive keyboard events and other events from it via the serial port. The serial port reports, say, data packets that contain a bit that tells you what you get, like a keyboard event or return from your some return status that you can inquire from the terminal and some other things. But well, it acts like a terminal, and the graphics commands are implemented on the ESP32. So all that line drawing that you will see, those are just BBC basic video codes. The video command set is implemented on the ESP32. And in Flash we run MOS. MOS is a kind of, well, BBC inspired operating system with some commands to display a directory, to load files into memory, to run commands. Well, it's, I think, even simpler than CP/M in that respect. But it's good enough to, and it implements FAT file access on an SD card. This thing has a micro SD card, so you can put all your programs on a micro SD card and just run your FORT stuff, run your programs, and your applications do have a way to read and write files, which is kind of essential. And BBC Basic is normally run on this thing. It's just loaded into RAM. It could have been in Flash also, but it's loaded into RAM, and you can leave BBC Basic and run your FORT, or not load it in the first place. So what's my history with FORT? Well, in 1987, I first implemented a FORT for the Z80 on the ZX Spectrum. The ZX Spectrum, you all know, that little British computer with 48 kilobytes of RAM, 32 column text display, and you could run interesting games on it. Basic was horribly slow. FORT was a way to do something more, to run faster code without going to assembly. So that, and I wrote a second FORT for it. That was meta-compiled, cross-compiled from the first FORT. So yeah, that was my first experience with FORT. Then in 1994, I wrote a SOT32. That's a virtual machine, stack-based virtual machine with some, well, geared to FORT. And then, of course, it had to run a FORT. I wrote a minimalist meta-compiler for it to run on it, and a FORT system to run on it. So I had a small FORT system to play with, to port from. I did port it, a port from that. 9 1989, I was already toying with the 6809. That last in 1995, I had an actual Ford running on the 6809, and it had a prefix assembler. If you're a real Forder, you have a postfix assembler, probably. Those do have advantages, but I found it very hard to read the machine code from it. March 2022, that's a long time later, I wrote a Ford, Z80 Ford on the Cerberus. I wanted to use the same meta compiling techniques that I used for the earlier Fords. That's why I mentioned them. Also had a prefix assembler on the Z80. That was quite a can of worms. Turned out to be, but well, got it running somewhat. And I took the assembly language primitives from CamelFord by Brad Rodriguez. That's why he's still mentioned in the copyright notice. Because these were a bit more efficient than what I had running on the Spectrum. So that's why. And then January 2023, I ported this Z80 Ford straight to Agon. It was a 16-bit Z80 application, just straight Z80 code. And it took me a few hours to get it going in the first place, just to, of course, the interfacing with keyboard and display were different. Took me a few days more, a weekend hackathon to get it really working on Agon. And then in July 2023, but it's not, I already worked on the design of that Ford way before, but I had nothing to run. In July 20, I started a 24-bit version of that Ford. That actually has a 24-bit word cell size. We call it cell size, not word size. And runs completely in easy ADL mode, the extended address mode, and can use all the RAM. And that's, well, that basically has the same feature set as the 16-bit Fords. I can run the programs that I have on one, I can run on the other. I want to extend this 24-bit Ford to be, say, more or less fully ANS compliant. I want to make some features that I really liked from earlier Fords, like the view command, that you can just type view and then your word and then you open it. The features like this. I do have an assembler in that Ford also, that I already have. So prefix assembler, that's what I have in these Fords. I took the idea from FPC. That's a Ford written in 1988 by Tom Zimmer. That was for MS-DOS. It had a prefix assembler, and when you opened the source files, you could read. If you knew your Intel assembly syntax, it looked very familiar. And I wanted that for, what I was programming 6809. I also wanted that a prefix assembler like that. And I wanted that for the Z80. And normally on the Z80 you have something like CW, BW, move, comma, or something. And I wanted something that looked more familiar, like LDB, comma, C. And what you have in the prefix assembler, basically each instruction executes a word like a semicolon. It was called in FPC. I kept that convention to assemble the previous instruction, and then the opcode, the opcode word like LD or add or JP that for jump sets some variables, also an instruction handler. So if the next instruction executes, it executes the correct instruction handler. A, B, comma, and C set operand variables. A semicolon executes the instruction handler and puts the instruction in memory. And then, of course, Z80, the LD instruction, has so many different varieties, like with IX and IY, with 8-bit registers like B and C, then some indirect indirect forms, and then the ones with HL are different from the LD BCA and LDA BC, and all these are all different. These are all over the place in the opcode map. It makes you mad. So that's, and of course the C comma word. C comma is LD C comma D. It's C comma, you want it to be a register, a destination register, but you also have these jump instructions like JR C comma some label. It's not nice. And then of course you also want C comma to mean what it normally means in Forth, like add a byte to the dictionary. So it's not the most elegant piece of software. It can definitely be more Forth, idiomatic Forth-like. But in the end I got it more or less working. So we have a direct threaded Forth. In the Z80 mode, I took the convention that Brad also used, like the instruction pointer is DE. The stack pointer is just the stack pointer of the CPU. The top of stack is in VC. The return pointer is in IX. And the next instruction, it's 7 bytes. The next word, execute the next word, XDHL. So HL now points to the, so the instruction pointer is now in HL. Then you do LDDEHL, INC HL, LDDHL, INC HL, XDHL, and jump HL. That's 7 instructions, 7 single byte instructions. And that's your quote. I inline that next routine. And that's, well, I think the optimum thing you can do on a straight Z80 with 16-bit addresses, with a straight Z80, with direct threaded code. You can, of course, I did contemplate, maybe I would, well, if I could fork myself into different hobby time budgets, I would do it. But I don't have, I have other things on my computer hobby time and I have a job. So I really would like to have a subroutine threaded forth with native compiled code. For the 24-bit Z80, you do have enough memory for the compiler, definitely. But I have a direct threaded forth right now. Its IP is in IY register, SP is SP, TOS is in DE, not in BC, because you need the ability to swap DE and HL because you're not having this, you cannot easily move a 24-bit register to a different 24-bit register. You have to move byte registers, but the upper byte you cannot move. But you do have XDEHL that works on the 24-bit register, fortunately. And now the next routine is using loading HL from the IY plus 0. Then it uses a LIA instruction, load effective address. It's basically increment add 3 to IY. That's what it does, and then the JPHL, and that's also 7 bytes. It's not much slower than the 60. I don't know exactly how much it was. I think it was in the same, nearly the same number of cycles as the 16-bit next. So yes, I went for that one. And now let's see, we can close this window. We can maybe do the Emacs now. The Emacs now to view some source code. I will continue to share the screen. Allow. What's next? Where is my? Do you see my Emacs window?
Nope.
No. I try to share again. I don't know what's sharing now. Never mind. That these are. I'm lost. Share doesn't. Do you see? That's embarrassing. I can't stop sharing.
No, you already stopped sharing. At this time, you are not sharing at all.
Yeah, the share button doesn't react to me anymore. Reds. Maybe help. Houston, we got a problem. I can reconnect to the Zoom meeting, but
you should see on bottom of the screen a green button.
Yes, I know. And if I press it, it does nothing. It's, oh yeah, there is this single, oh yeah, that window went under another window. So now I can share. Oh. But now you should see my Emacs window. Do you?
No, not yet.
I thought.
I see Tom Zimmer. Hello, Tom.
Yeah.
Oh, hi.
Oh, I can't stop sharing. There's something.
I suspect you have your share control windows on with the button.
Yeah, I
hanging
have
somewhere.
one. I selected the Emacs window, but that's no. I try to get to now I oh. So now
You have to select the Emacs window.
Yes.
Then hit the share button, and then and only then does it go live.
Yeah. But I'm now complete. I'd have to sorry, I want to I don't have time for I hope I can reconnect because my sharing is now completely wedged. I don't see a stop sharing. I don't see I try to leave the conf call and join right back in, but that will take some time.
This meeting is being recorded.
Yeah. Am I back in the meeting?
Yes, you are back.
Yes, you are.
Now I'm going straight into the Agon Lite emulator. And now and now I have to use a single window and Agon Lite emulator, share, and hopefully that will share now.
Absolutely.
Finally, ly. Nerve-wracking experience with that. So we go into the Fort, and we are now in the Fort. The 24-bit Fort. So if I do -1 U point, we get a 16 million figure. So that's 24-bit. I can open, say, the kernel a.fort. The editor itself is not written in Fort. I wrote that in, this is the editor. I can start it from Fort. So what I wish I could show you in Emacs, I show now in yeah, these are this is the source code of this Fort. So like do call, do var, you know, all that stuff that's near the start of the dictionary. These are all assembly code things. You see, I use the IY for instruction pointer, and yeah, and for the exit, I do load IY from the IX. That this IX is the return stack pointer, and then I increment IX, and then I do a next. It's very straightforward. What's not so straightforward if we do a, well, definitely not the multiply routine. It's very convoluted. I want to collect all the operands in 8-bit registers that I can access, and I have to move them to a register pair and then do the multiply instruction like multipc, and then save the results to put other. This one is kind of a sliding puzzle nightmare. I'm pretty sure somebody with more experience in easy-80 assembly can do it in half the instructions. And is a little less complex, but for bitwise AND, there's no way we can access the upper bytes of the HL and the E registers. So the most significant bytes for you have H for bits 15 to 8. You have L for bits 7 to 0, but there's no byte register for bits 23 to 16. That sucks. So we have to store it just below these operands just below the return stack. Load A from that address. Do the AND then in memory. Store it in the yes, and the upper bytes, and then store it back where we want it. Yeah. I don't know why it's -1. That had a reason, I don't know. That's not right. I don't know. I ended the upper bytes and wait, I know. That can be right, but I tested these routines, so they work. Don't know. Well, that's a Schrödinger bug. I stored the byte back at the wrong offset, but these things have worked. So I'm not totally happy with that. These sorry. I've how can sweat. I don't know. That should be -3 IX, but these routines have been tested, so they should work. I don't know why they work. Good question. Anyway, maybe this is so. We have, on a lighter note, we have Turbo graphics. Graphics with yeah, we open that in editor. We have turtle graphics, we have a sine table, sines of all angles in degrees. Cosine. No, I'm totally lost. Yeah, we have this whole turtle graphics. Say we want to yeah, go forward. Of course, that's important. That we the distance we multiply by cosine, and then do some scaling. Calculate the remainder of the bits left over. We take these into account. So when you move forward, you do an equilateral triangle and you move forward distance 500 and then do a 120-degree rotate and then another 120-degree 500. You end up in the same point. You're not drifting. We shall see that if we open float GRP demo. Run demo. Now this first started out with color text. We have an 80 columns, 16 rows of text. Now we can draw colored lines, whole screen full of it. Now we have some, say, polygon circles with turtle graphics. These are spiral. These are quite interesting figures. You draw polygons in closed polygons, returning at the same starting point. Then turning left or right, and then increasing the size of the next polygon. So you get these polygon spiral things. These give somewhat interesting figures here. It's, well, Lissajous figures. And then the trees. This is code that was originally invented by one of the Dutch old guard forters, Kees Moerman. That was published, I think, in 1990 or so, thereabout 1980 something, I think late 80s. And I found it very cool to recreate that tree drawing algorithm with turtle graphics on the Agon Lite. And it's just, yeah. Probably drawn in a higher resolution than he even could have. I had that one on my PC back in the day. Those are turtle graphics, trees and so. Oh yeah, I'm a bit overstepping my time budget. I still want to show one game by load Forth 24-bit bin run serpent no, that now I'm going on. That's a snake game. And now it's still easy to grab the foods, but if your snake gets longer and has lots, and then it gets tricky to get the foods that are near the edge of the screen. I could show the source code of that one, probably. But I think we have to do the question section now. Shouldn't we? Does anybody have questions?
Well, more than a question, I want to make a remark that this presentation was excellent. I am really impressed with the speed of this single board computer and your force.
Well, yeah, this thing is probably like a 50 megahertz Z80. But one thing is there's an ESP32 inside that does all the line drawing. So these are just character-based, this snake game is just character-based graphics. Old school stuff that you did on an old pad computer. But now we are doing it on the Agon Lite, and you can redefine the characters. That's what the ESP32 supports. You just send your 8x8-bit pattern as a few bytes to that thing. So part of the speed of Agon is certainly that the graphics is handled by the ESP32.
Another question I have, Lennart. Sorry to interrupt. What about the hardware? Is it possible to talk to the ports? Do you have pins in the board?
Yeah, there are ports, but so far I've never experimented with them. But of course, it's possible to just say have a P store, P fetch to get to these in and out instructions and write directly to the ports and do everything on top of it in Forth. Or while you're at
before your presentation, I was explaining to the group about this Agon computer, but I don't own one. And I was saying it's similar to a Raspberry Pi.
No, it's not similar to it has two CPUs inside. What's different from the Raspberry Pi is that Raspberry Pi you boot into Linux. And Linux, even if you have a very low-end system, there are hundreds of processes running behind your back.
Yes. No, I'm not saying that the software is the same. I mean the size, and if you have a port, you can make retro computing talking to hardware also with force.
Yeah, the Agon computer has, say, an I/O connector that you can connect the parallel ports. I think one of the SPI ports, I2C, you can configure the hardware to do all these things. And with the aid of assembly language, if you want to have fast responding interrupt routines, you can make all this happen in Forth also.
Amazing. That was my question. Yes, exactly.
Yes. And yeah,
Do you have your source code on GitHub or something?
yes, I have it on GitHub. It's I can post a GitHub link to on the chat window. But I think I already over used my time like the previous presenter. So let's move on.
Okay, fantastic.
Thank
Nice
you.
presentation. So, gentlemen, the next participant, I don't know if we have Greg Bailey in the meeting. Is Greg Bailey with us?
Skipping me?
No, you are there, yeah, but I'm asking only about if we don't see him. Okay, James. Next participant, James Norris, T-FPGA board, assembler for ESP32, the upper glue and force news. A lot of stuff. Go ahead, James.
Let's see, since the last time I did a presentation, the elevator challenge, I made an HC11 assembler, fourth assembler. I made a 6502 fourth assembler. I mirrored diaper glue under the FORTH 2020 repository, so you can look at it there. And I'm working on an assembler for this board. And I just got this in the mail a couple days ago. So I haven't been able to test it or anything. I have all the extension instructions and it was pretty easy to do. I'm only going to support the little endian syntax for now because I don't quite understand how the big endian syntax works because they have instructions in there that look like they won't work if you're in big endian mode, and I couldn't find anything in the documentation that verified that. So right now I'm trying to figure out how I want to test the assembler on this. The easy way to go would be to just do it the way everyone else does it with the Arduino and have all that stuff on there, and then use ESP32 fourth to test my assembler. But I would really like to do is just have as little as possible and have the assembler go on there. They have a direct boot up, but that means rewriting all the drivers and everything. And then there's a level where you can go to the operating system, and I'm trying to find the documentation for all those words. It might be possible to talk directly to the IO routines. The hello world that they have uses C and the C library and using a printf. And that's like, printf, why would they have a printf? That's pretty high level. I would like to do something lower. That's pretty much where things are at. Does anyone have any questions? Wasn't able to test anything yet. I'm still typing in all the code. What I suppose I could say is what I'm going to do is I have all the extensa instructions in. So it's just like you just use the register names with the extensa opcodes. They have a RISC-V version. I'm not doing that yet because I know it's not on that board. What I'm going to do is put on top of it the standard. If anyone's looked at any of my assemblers, it's going to have the assembler syntax that I have in my other assemblers. I'm trying to kind of make a cross-platform assembler. We have a set of core instructions that will work across all of them. I ran into an issue with the extensa instruction set that it does not support things like overflows or flag registers or anything like that. Instead, they combine the test of the registers with the branch. That would be portable to the other assemblers, but then the stuff that the other assemblers can do won't work on the extensa. So like if you want to branch on carry, well, they don't have carry, so you can't do that. They do have a branch on greater than, but they also compare the registers and then branch on greater than, which would go the other way. And that's, did I get everything you wanted me to say, Peter? Because
yes, just explaining the T-FPGA, why you choose it, and what are your goals with this board.
Oh, I chose this because that's the one that you were using and a couple other people in the group were using. I wanted to pick one that had ESP32 running on it, the ESP234 running on it. And then they could use my assembler to generate assembly code that they could use in their projects. That's pretty much what I wanted to do. And the way I'm writing my assembler is I'm trying to avoid as many diaper glue specific words as possible so that you can use this assembler on any forth.
Looks great. And who else? It's Jason. Jason probably has any questions about the FPGA part.
It's that's the Tang FPGA, I think, right?
Oh, I'm not writing anything for the FPGA yet.
Yeah. Okay, so you haven't touched it yet. I was just curious about what the experience was like.
I'm really looking forward to playing with it because I wrote a microcore in college and I never got to test it out. And I was gonna, this has 4,000 LUTs on it, so it should be enough to do at least part of it. I could definitely do. I'm really looking forward to trying it and see if I can get it to work. But I would just use, you can directly program the LUTs. You can just say what you want. So that's what I was going to do, is put the numbers in for the, when I was in college, I learned how to do that. So you just tell what the destination spec sources, you say what the multiplexers are going to pick as their source.
Yeah. Yeah.
Give it the bit pattern for that.
Yeah.
So, you know, I like most of the VDL stuff, they have all these and things to make it easier for you. Like, oh, I want to do this plus this equals that. And then they figure out where to put it. And I was like, well, you can just do it yourself.
There was a period back there when everybody had a small fright because I think that the Tang FPGA stuff, the software that they use, you have to request a free license, and the license server disappeared for a while.
You don't really need one. Scare. Well, this is what my degree was in college. So, and they didn't have any of that back then. So what we learned to do was you just said, you have your states and it's a state machine. And for each state, you say what the inputs are for your combinational logic circuits, and you say what combinational logic circuits are. And then you have to, this is the part they make it easy for you. You have to, it's two states. You have the NANDs, and then the two levels of NANDs gives you your where you pick your sources for you, and then you OR them together. So then once you have that, that's your bit pattern, and you just put that into your ROM for the FPGA. I'm not exactly sure how to do that on this particular board, but I do know how to do that. So I was going to try and do it that way. And so you start off with your statements like this register, it gets loaded with this register or this register based on these bits. So if it's a 1, you pick this register. If it's a 0, you pick this register. If it's a 2, you use this, which is this combinational logic, which is an adder. And then the LUTs have bit patterns that you tell them that does that. And you just put the bit patterns in the ROM.
But then that means the bit stream is documented, is it? I didn't know that.
I think so. I didn't quite get that far in the LilyGo. They were talking about these had the LUTs, and they said it gets loaded into a ROM. So if you know how to put the bits into the ROM, you can do it.
Yeah.
What I am not sure, if you can start with just buying the TFPGA board, or you need a carrier. There is a carrier board also.
I think you can, because there's 2 ports on this one. This one has two USB ports. One is for programming the extensa. The other one is the JTAG FPGA port. And if you have JTAG, you can put the bits in anywhere you want.
Oh, okay.
So I'm pretty sure using JTAG, you can program everything any way you want. I don't know how to do that though.
Interesting, really interesting. Okay, James, then if you don't have anything else to say, are there any questions?
Did anyone look at my assemblers that I wrote? Any of them?
Didn't see
Oh.
it, but I'd be interested to see.
They're mirrored on the Forth 2020 repository. So you can look at them there. Guess that's it.
Well, this is the way we like it. When someone in the group has something to say or wants to exchange, oh, guys, I bought this, I am interested to develop something, just raise your hand and participate with us, and everyone listens. And we all learn as in a club. Thank you so much, James. Who else is the next one? I think it's Greg Bailey is not in the meeting. Is Greg in the meeting? Then we move to the next participant. Jos Ven will show us sorting tables in Forth. Jos, are you ready?
Yes, thank you. Am I
Go
clear
ahead.
to explain? Is my sound okay? Okay, thank you. Then I'd like to share my screen. Okay. Even kijken, deze is het. I'm going to talk about the tables, and in this case, all records have the same size. Address pointers are used to access the records, and I use a tool to access the records in the table, and I made a small demo to demonstrate its use. The tool has the following advantages. It uses relative pointers, so there's no need to generate the same address pointers again when they are saved in the file. That saves a lot of time, since you don't have to build them and you don't have to resort the same table. Multiple keys can be used to sort the table in one go. I have the following sorts. There's a string sort, there's a binary sort for numbers, there's a float sort for floating point numbers, and each key can be ascending or descending. Then there are also macros to access the records in a table, and it is also possible to sort different tables parallel. In that case, you need preemptive multitasking. The system is tested under CForth, GForth, and Win32Forth. Well, let's look at the code for the record definition, allocation, output, input, checks, and manipulation. Here's the source. First, there are a number of tools to be able to randomize the records in the table. And there is also a word to extract a number from a counted string. For the record definition, you need first to define a value that points to the table. And then you have to determine the sizes for the various fields. In this case, I use a counted string for a name, an integer for a group, a fixed string for a phone, and one extra field that is reserved for the future. Next, you need to define a structure to get to the various fields. In this case, again, for the name, group, phone, and the reserved fields. Then you have to define a key with the word key column. Key column needs the position in the record, the size of the field, if you use a counted string, then you have to skip the count, otherwise the sort goes wrong. Then you specify a name, and with that name you can sort up, down, and determine what kind of sort must be used. Of course, you need to allocate some memory. In this case, I use allocate records, and that allocates the memory for the records, the pointers, and stores the table properties. When you are ready, you can remove the table from the memory, and of course, you can erase the table. These steps work as follows. First, you have to initialize the table. Then you can, of course, allocate the records. And the next step is to erase the table. So you have a clean start. If I compile this file, you will see the following. It has loaded a table, a new table with new records in the memory. It starts at this address. Oh, sorry. It starts at at the first. Sorry, at that number. That is the list of records. Then there is a list of address pointers. At this moment, there are only 8 records loaded, so we can easily see what happens. The record size is 44, and the table size is then 352. To give you an impression, I can show you the records. That's done by giving a table of the name table and the records. Here you see them. The names are all randomly all random. The group is random and the phone is also random. Now go back. Oh, that's about output. Now, dot records we have seen dot records to show the tables unsorted. There's also a way to see these records sorted. It works the same way, just another command. For the input, in this case, I use randomize records to randomize all records in the table. Then I made some checks. The most important is check table. Check table can be used when the table is sorted by group, name, and both must be sorted ascending. I did this to check if my application works right, and there are no stupid things. Then you can also make modifications with the word input test record. Again, in this case, you must say which record must be changed, and then the program will ask for the name, group, and phone. The input is going to an inline record. So if you make a mistake in the input, then your table will not be damaged. There's also a possibility to save the table and load the table. Even kijken. Simply by calling save table and load table. And of course, there is also a kind of manipulation to sort the records in various ways. Now let's see what may happen. Here you see that the group numbers are not sorted. So I would like to sort the group numbers, and then within the group numbers, the names from down to up ascending. Here we go. And as you see now, the groups are sorted by its number, and then the names are sorted within that group. If you are going a bit deeper in the system, then you can also say, I would like to see the address of a record. Well, first task is to get the address of the record. Note, this is a relative number, so it's not the actual address of the record. You need to add the address of the table. That's done in this piece. And now you get the address of the record. And to make it done, simply add the following piece. And there it is, RZS, and here also RZS is the same number. That's needed sometimes when you like to see what's going on in your table. To see a record, there's also another way. You can simply say the first record of the table, and NT to record will then produce the address of the record, and dot record will print the record. Okay, well, let's change one record. It asked for the name. Let's say it's Peter. For the group, 0, and the phone, we take this one. Then, if I say show the records unsorted, Peter is at the top. And if I say, even kijken, sort the table and show the table. Yeah, okay. Peter is still at the top since it's group 0, and Peter is with a capital, so that's the first letter in the table. Sorry. Okay. Then the next step. Even kijken, start, save. Oh yeah, that's this line. If you would like to save the table, well, okay. Oh, dat klopt niet helemaal. Dat moet dit zijn. Moment. Even kijken. Save. Okay. This piece will save the table. You need to specify the name, the count of the name, and the table. Paste. And now the table is saved. And to prove that to you, I will random the table. And as you see, Peter is not more in the table. And if I load the table, loads. By using this piece, it's the same name, table name, count, and record size. And I save the table in the value, otherwise the system doesn't know where the table is. And if I enter TS to sort and show the table, then Peter is again at the top with all the other records. It's perhaps also fun to see the tool. I use a shell sort. The macros are defined at the top for GForth or Win32Forth, and it can also be used for CForth. Then the macros continue, and the most interesting part is actually the table sort. Well, it uses a shell sort, and as you see, you can specify a number of keys on the stack, say how many keys you have put on the stack, and then the name table, and it will sort the table. Of course, you can also do a much simpler version. Nou, dat is wat ik bedoel hier. Even kijken. If I would like to sort the whole table with only one key, that's this one. Oh, sorry. And then you see it's again sorted by name, and this time only by the name and not by the group. It's also possible to change the key and show the key. Wacht even, dat is deze. Oh. And now you see that the group number is sorted from up to down. So 2 is at the top and 0 is at the bottom. Well, that's actually the program. Are there any questions? Okay, if you think, well, these are only 8 records. I have also a demo, which contains a few more. Nou, even kijken, is het? Table sort. Table test. And here I have nee, dat is de verkeerde. Kijk, het table test sort. Well, yeah, it is. Here I have 2000. Well, that's not much. Let's add the 0 and see what happens. I've now, oh yeah, it's a bit fast. There are now 200,000 records loaded. Each record size is 12. Table size is 2,400,000. And first I sort the files. Sorry, I sort the table. Even kijken. Oh yeah, first they are sorted individual, dus one for one, and that takes about 3 seconds. The next sort is again a sort for the 4 tables, but in this case I sort them all parallel. And now I need only 800 microseconds to sort them. So that saves a lot of time. Oh, niet gesleept dat geloof ik. Even kijken, soort key. Each table. Oh yeah, the next step is to see what happens if you sort the same table again. In the first case, all 4 tables are sorted again. So nothing is changing, and then you need not 3 seconds, but only 832 milliseconds. And if you sort them parallel, then you only need 171 milliseconds. So you can actually sort and manipulate tables quite fast. And if you need more, then it's also possible to use memory mapped files. Then you don't have to load any data at all, and you can directly access the system. I have here a small example. Some may have seen it before. Kom, oh, hij doet het niet. Ah ja, daar is die. Hey. We do it again. Oh, in this case, there are 350,000 records loaded. And they are already sorted, and they are already loaded. And yeah, as you see, that went quite fast. In this case, I get records. Each record, contains the temperature, humidity, pressure, light, and Wi-Fi signal, starting from January the 7th until September 9, and each day of each time, each minute, a sample is taken, and that's accumulated in this table. Well, that is how you can handle records with my tool. I hope you like it. Are there any questions, or is it all clear?
Christian, do you have any questions?
No, Peter, I don't have any questions.
Then we have a problem.
I have a question I've got here.
Okay.
I don't know if you, thank you very much for the presentation. It was absolutely interesting. Have you ever considered running like a benchmark with, I don't know, Python or whatever other language to do the same sorting with the same type of data? I would be very, very much interested in the speed of other languages.
No, I don't know. No, I haven't done that. The main reason to make it was actually to be able to handle tables in a small system.
Yeah, indeed, understand.
And yeah, this is a quite small. So I have no idea.
Yeah, absolutely understand.
If you are interested, I can also even kijken, put the links to the files in the chat, so you can play with it yourself.
Well, why not? I would be I would be keen to play around with it, with the data, with the same data table, and then let's see what it comes
Oké.
out.
Scherm stoppen. Even kijken. Moment. Here they are.
All right, thank you.
And it is a really easy system, I think, to manipulate records and tables and all kinds of things. Well, thank you all.
All right.
Very good.
Excellent. Thank you very
Nice.
much.
Nice, Jos. Thank you so much. Pablo Reda has no question, and Alex Dumont, no questions. Or Mateo Vituri, no questions.
No question. It was very interesting, yes.
Jos, you use shell sort. I have implemented radix sort too. It's more easy to code. If you like, I send the code, but it's in MyForth.
Put it on the Facebook group, Pablo.
Okay. Very nice, Jos.
Yeah. Now the reason that I use a shell sort is as follows. I needed some kind of so that is reasonable stable. And when I got the code, it was only able to sort on one key. And I also would like to be able to use multiple keys. And when I compared the various sorts, then the shell sort was the easiest way to get that accomplished. And that's actually the main reason.
Excellent. Then we can move on to the next speaker, who is James O'Brien. James, are you in the meeting?
Yeah, it's John O'Brien.
Oh, sorry. Are you presenting your kit, your MyForth? Excellent.
Not my kit, but I built it. This is the MyForth board. The website is mynor.org, mynor.org. It's an 8-bit discrete logic computer created by Dennis Kuschel. I might have killed that last name, from Germany. It's built. There's no CPU. It's all discrete 74 series logic. This particular one runs at 10 megahertz, and it's got 32K of ROM, 32K of RAM, and there are a couple of tiny little EEPROMs for storing block code. It has 6 digital input pins and 5 digital output pins. The pins are shared with an I2C bus, so you don't get a full 8 input and output pins. They can also connect RS-232. The I2C implementation supports Adafruit stemmas and the SparkFun Quick formats. The through these pin headers here on the side, which you can also use with an FTDI cable. It's not standard layout for, like, when you buy the FTDIs with a single block, it won't just plug in there. You need the one with the separate pins and figure out which goes where. The board is pretty power hungry. To run it, I have to use an external power supply. I tried running the output pins to a breadboard with some LEDs, and it running it the board from the USB ports on the laptop, even USB-C, was not giving it enough juice to run the board. I didn't hook it through an ammeter to see how much power it actually takes, but it needs an external power supply. There's a micro USB plug here for power. It can also be powered through the FPGA and I2C pins here. It's a tiny little thing. It's 10 centimeters square. Yeah, the kit went together pretty good. It was I don't know if it was 50 euro. I forget offhand. To run it, I ran out of USB ports on the laptop. I've got a USB to RS-232, and then a micro USB going over to an Apple iPhone charger. And if I can share, that should come up in my terminal, to my terminal.
I have a quick question. Is that 7400 HCT components?
74HC, yep. There are, he specs different component, you can run at different clock speeds, and in the documentation he specs different components for higher clock speeds, and actually cautions against using the fastest chips possible in some clock speeds, because it's sometimes they're too fast and the machine will trip up. Hopefully you guys can see all this. I've got two EEPROMs on the board. Standard, it comes with one. I happen to have a spare one in my my parts bin, so I grabbed that. I do have a oh, let's see. There we go. Okay. If you run into a low power situation, it just does not recognize the command. You'll type a command, it'll say unknown command, and that I found that out quickly. If you're not feeding enough energy, I can load a program from EEPROM. And this is a game available on the website. It's 2048. Some people may be familiar. He got the code from the Rosetta code project and ported it to this version of Forth. And here you're trying to move the blocks to get to 2048. So using the arrow keys or the WASD, you combine the numbers and you're trying to build blocks up to 2048 without running out of empty spaces to move. And it's for as simple as it is and as fast as it, you know, there's no actual CPU, it's just discrete logic. The microcode is taken care of in ROM, and there's one NOR gate that kind of acts as an ALU. MyForth is kind of a pun because it runs forth, but it's also this guy's fourth design for discrete logic CPUs. And so this game just kind of goes on and on like that until you lose or win. I haven't won yet. I don't know if it's possible. I've come close. But reset there, and let's see. It's a 16-bit Forth system. It supports the Forth 2012 standard. Core and extension words, double number word sets, block word sets. It's got a built-in text editor. So if I go 10, edit, this is that game. Or one screen of it. It goes on for about 4 screens. And yeah, it's a nice little machine. A little bit about me. I started electronics when I was real young. I used to buy broken things at Radio Shack, fix them and sell them. Got my ham license when I was 16. Went to school for electrical engineering, but I joined the army to pay for that and had to go overseas to the former Yugoslavia, and that really put a crimp in my college career. So I ended up not graduating with electrical engineering. But I've been a computer and electronics hobbyist my pretty much entire life. I learned to code HC11 assembly and C in college, but I don't do it for a living, haven't done it for a living. So I really got into retro computing and building kits. On my workbench right now, I have a Spare Time Gizmos ELF 2000. I've got a Z80 single board computer, the N8 VEM, which is now Retro Brew. I've got an RC 2014, a couple other things. Oh, and Peter from Australia is in here. I posted this in the Facebook group yesterday. I found this little guy, Parallax P8X32A quick start board. This was a pocket microcomputer, pocket mini computer from Propeller Powered, which the website no longer exists. So I said, gee, I wonder if I could put Forth on that. And I found that Peter in Australia has Tachyon. So so this little machine has Tachyon on it now. I haven't played too much with that. But yeah, if I was designing the MyForth board, I do a couple of things a little different. But it's great for what it is. The power thing's an issue. The non-standard pin layout is an issue for me. But it's fast, it's responsive. And I mean, it's not tiny like an ESP32 or even that propeller, but yep, I think it's a neat thing, and I'm happy to share it.
It's quite amazing that such a little board, almost without CPU, without anything, it runs so well and so fast.
Yep, I'll pop the link in the chat if I can figure out how to get out of here.
Benchmarks. We need benchmarks.
Oh, sorry. Okay, project for next time.
Yeah, that's a good question. What's the next project?
Well, my next project is getting over COVID. I just about made it to the meeting today.
Wow.
So I've been in rough shape this week. I was planning on doing a little better, but yep, I think that's it unless there are any other questions. Like I said, I didn't create the board. I just built it and kicked it around a little bit. Go ahead.
Do you have a feel for, can it execute the Forth code at one clock cycle, or sometimes it takes more than one clock? It's decoding the EEPROM or the instruction.
Yeah, it takes it's the crystal. It's running at 10 megahertz, but it takes a couple of clock cycles to process the instruction. It's like this is like a 1-bit ALU in there basically, and I mean my reference points are in RCA 1802 running at about 1 megahertz and a Z80 running at 4 megahertz. So for my other Forth experiences, and it seems faster than those, but that could be. I mean, I'm running the Z80. I'm running Forth under CPM. the 1802 runs RC4th, I believe.
I had one of those. I had a Cosmac L.
Yeah, I built the L2K, and then there's a board out there, the recreation or recreation, another pun board. I built a couple of those where they've taken the I forget the guy's name, but he's taken the original schematic from Popular Electronics, made a circuit board from it, and I actually found a destroyed ELF on eBay with chips that are some of them older than me. The CPU is from the 11th week of 76, and I'm from the 4th week of 76. So it's, but I was able to get them
there.
I think Klaus, I don't know if Klaus is listening to the meeting, but he knows more about the speed. I know this is a single, this is a 1-bit only arithmetic logic unit done.
Yep.
And it's really it's a very slow computer, but this guy has made a fantastic job with force. He has developed a force that is a lightning, and this is why it's speedy. In the end, it appears it's a very fast system for the architecture. The architecture is very tiny.
Yeah, we really shouldn't be looking at this on the. I'm just curious about the speed. It's all about the fact that he did it in TTL. That's amazing. That's really cool. Yeah. So speed really isn't that important. I'm just curious.
Well, but he did this also in transistors, not only in TTL, Dennis.
A lot of transistors.
This is how it began. It began in transistors, and he made a board. It's a sandwich of 4 boards with SMD transistors. It's not so big.
Yeah,
wow.
And this is his 4th iteration, so it's a play on words. MyForth. It runs 4th, but it's also his 4th iteration of this discrete CPU idea.
Very cool.
Yes, it's amazing.
Someone in one of the forums was someone gave a count of how many transistors this ends up being with all the chips, and someone else was in one of the online, I don't know if it was Reddit or wherever, I just remember reading it. Someone was gasping at the fact that there's fewer transistors in here than a 6502, but not by much. And oh, well, you can do all this other stuff with a 6502, and the thread was old and locked for some. The thread was locked. I couldn't reply to it, but I mean, yes, this might have just fewer transistors than a 6502, but a 6502 needs all kinds of other chips to run. This is complete in and of itself. That's the thing.
That's the thing, exactly. This is a complete computer, single board computer, not only a CPU.
Yep.
Oh, it's really a fantastic presentation, and this is the objective of the group. We want to have everyone talking about what they did in the months, in the week, or during the last time, so other people get interested and then go after Minor, or go after Agon, or go after the project of Dawn, of the Core 1, or go after Jos work, etc. That we present what we were working during the last time, without much reverence and without much work.
I can give you a 5-minute update on Core 1. So the boards are being fabricated right now.
But later, Don, because we.
Oh, okay. You got another presentation. Okay.
Yes. We have a lot of presentations. I give you the last part of the meeting if you want. We have now a coffee break. So, okay. During the coffee break, if you want to talk about the core one, it's no problem. I am going to a coffee break of 10 minutes or 15 minutes, you decide.
Yeah, I just the boards will be assembled next week, and I should have them at the next meeting. That's my update.
Cool. Okay, we shall now go off the record for the coffee break. Recording will be paused. Remember, you are now back to being supervised. The next presenter is Bill Ragsdale with the evolution of Create Does over 40 years. Bill, have at it.
Very good. Thank you so much. And let me go to share screen. And we are now live. So by way of introduction, Bill Ragsdale here. I was the founding president of the Forth Interest Group and wrote the FPGA model and used Forth for 25 years in commerce and then retired. And I'm now devoted to Win32 Forth. More about that later. So today we're going to talk about the Create Does over the history. It started out as Bill's Does, 1968. This was the original development by Chuck. Notice it uses Bill's where we use Create today. In 1982, Chuck came up with an inspiration. We'll talk about it in a little bit as spur of the moment, and he simplified it down to be a Create Does format. And then now in Win32 Forth, in the versions we see today, 2023, there's a slightly new variation on that. And this was introduced in probably year 2000 or a little bit before by Tom Zimmer and Andrew McEwen when they did Win32 Forth. So what does Create Does do? Well, it's a word that creates words that create words. It's the third level of Forth. You can look at words that exist, you can look at words that create, and then you can look at words that create words. The Create Does format can actually be used for the primitives within Forths, for example, such as doing constant variables, arrays, and so on. And also, you can use it to create database fields. It's very effective for that. And it's commonly used to generate assembler opcodes. And we find that Create Does is used when you find a family of words that have a common similarity. For example, the opcodes in assembly development are structurally very, very similar, but they just have various parameters in the different words. So Create Does works very well for that. So let's examine the levels. First, at the parent level, we have a word at the parent level which will create child words. And here is a parent word using Create Does. Create will build a header for a word, and then the comma puts a single parameter in memory. When the child word comes along that is created later, the does part executes, and the fetch sign will fetch that parameter from the parameter field. And this case is a demonstration, so we'll just drop that word. So again, what we have is a proto constant, if you will, and we'll see how this would generate constant in just a moment. The example down below is a hex number 1234. The parent executes, it generates the child word. The child word, when it executes, will recover that 1234 and then drop it. As an example of how this would be used to create a constant, the constant defining word, named constant, will create a header, save the parameter, and then assign the does field to the child word. And here we see an example with a hex 10 being with the word hex base being declared as a constant. If we're generating an opcode, it's rather similar. We would create the opcode. We would put a parameter in line. When that child word executes, it will fetch the parameter and compile it with the comma. So below we see the hex value 5F. We generated an opcode and we've assigned that to clear carry. So CLC clear carry bit with a comma. In fourth assemblers, the comma traditionally signifies the point of generation of code. The next word generated is the hex BB, and the opcode word would generate the word push, which in this case would push the stack pointer. And again, the comma says this is generating code. Here's a little more involved example, rather clever. This is to generate fields in an array. If we imagine we've allocated a few hundred bytes, and within that we want to set named fields. Each field will be generated by the word field. The create over comma plus increments an offset value and stores it associated with each field name. When the field name executes, it will fetch that parameter. It will add an offset, and the offset is from our original field base. So in the example, 020 field name creates a dictionary entry for name. It assigns it the 0 position in the array, and then it generates an offset 20 bytes ahead. That's passed to the next definition, which is cell field age. In this case, field generates a field named age, and it uses the previous offset and a cell value of 4 to assign a 4-byte cell for age. The weight field comes along, it continues the offset, and it assigns a 4-byte field for weight. So we have generated here in 2 lines of code a very simple linear array database. At the end, the drop occurs because there is an incremental value that's being accumulated as as the fields are generated. So here we see 3 examples of create does, where within 1 or 2 lines of code we have created an entire new class of words. A little bit of history on this now. In the 1960s, the form was created by Charles Moore, and it was created in that form until exactly 1982. In Chuck's original form, a parent word would use the greater than bill sign, comma, does, fetch, drop, as the example we saw before. The difference being that the word bills is what we now have come to call create. The child word in this case is a hex value 1, 2, 3, 4. The parent word executes, generates childs, assigns in the parameter field a value 1, 2, 3, 4. And the code that will execute for child follows does. In the blue at the bottom is how this appears when compiled into memory. You have the dictionary header, the word do colon in line, bills, comma, does, and all of these words are executed directly in line. Bang, 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 they are compiled. The key value here is during this compilation in the child word, the do does, it replaces the header. So in this case, when the child executes, it will execute do does, and do does reaches ahead in line to the next 4 bytes, and it extracts the address of the does part above and then interprets that. So the key thing here is that following do does in the parameter field, there is this extra pointer that occurs before the parameter. Now this was irritating historically because we had that extra pointer that was stuck in there, which is unexpected to be in the parameter field. This is the implementation out of FigForth. We can see that in this case, Bills does nothing more than generate the header and then assigns a single, reserves a single parameter field value by in placing 0. The does part comes along and it uses a semicolon code variation. And so we won't go through all the code in this case, but the does word is a immediate word. It rewrites the PFA, puts in its place do colon, and it also rewrites the code field address pointing to the do does code. So, and then the semicolon code is the runtime code. What we would call that these days do does. That is the actual runtime code. So, 1982, we were at the formal meeting in Asilomar. I'll mention that a little bit more in a moment. When this innovation occurred to Chuck, and he revealed it to the aggregation that was there. We see our similar example we have here now. We're using a parent word to create a child word, assign it the value 1, 2, 3, 4, just as we did before. But now in this case, the value of the do colon executes. Now the header is formed, do colon is assigned, create comma is compiled in line, and then a new variation on do does. It's paren do does greater than paren. That is the smart word that that innovates this, and it follows in line in the definition of the parent word, the here plus cell JSR do does. This is a very clever structure that actually simulates in line a very simple short code word. If you look at here plus cell pointing to code, that is a 2-cell code routine. In the executing code, then, when a child comes along, the child has a code field address that points back to that little inline simulated piece of code. And all it does is does a jump subroutine to do does. And do does actually does the work. But notice in this case, in the child word now, the extra parameter is no longer there. You have the code field address, and then you have the stored parameter 1, 2, 3, 4. But that extra pointer down there with the red arrow on it is no longer needed. So now we have a very regular structure. The keyword is done by that little pretend code word that's compiled end line. So the advantage at this point now, we no longer need the word bills, because remember, bills created the header, but it also reserved 1 cell of memory. Create replaces that, and it does not need to reserve that extra cell of memory. Extra pointer is not there. Another small benefit is that if we are ticking a child word, we will get the parameter address correctly where the parameter is stored. Whereas in the past, we would have gotten a cell that's performing a function, and we would had to offset the tick by 1 cell. And that was an irregularity in it that was overcome. Now we come to Win32.4. There's a major structural component that guides this, and that is that Win32.4 has all machine codes segregated in memory allocation. The headers and the bodies are in one segment of memory, and all machine code must be in another section. So this means that we cannot put that little fragment of simulated inline code in the high-level definition. It's got to be segregated down into machine code. So the answer that was come up with Tom Zimmerman, Andrew McEwen, was to increase the complexity slightly. It does not increase the speed of the time of execution. It's the same execution time, but the structure is a little different. And this is how the runtime portion for the child word is located. The key to this is that this word paren, do, does, paren generates a little code fragment, and I'm calling it the proto do, does. It is a little fragment that leads into do, does, and it locates the runtime code. So in that proto do, does, it puts in the code area the simple instruction to move to register W the execution address in the parent. This is compiled as a literal value at compile time. So at compile time, we know the location of the execution code in the parent, and that is placed in line, and it will be added at runtime, locating where the code should be. Then the system compiles a long relative jump to existing do colon. And the do colon places the child's parameter field on the stack and directs the execution to the high-level code in the parent. This is an example of what it would look like compiled. We see the parent header has a create comma, then that do does is located here, and it compiles the proto does, and then the high-level definition is ending by unnest, and our child word that we would execute. When this runs, here's what happens. The child word executes. The pointer to proto does points to the code area. The little proto does routine does, as I just mentioned a moment ago, it loads into the W register the execution address where the code is located, and then it goes to do does, and we see down below the normal process. We make room on the stack. The interpretive pointer is pushed to the return stack. We load the new interpretive pointer, get the address, and so on down. So you see the code now redirects itself to execute back up at the execution will go back up at the drop unnest part. So the green arrow points up to the @ drop unnest. That's the runtime code for the child word. So the advantage in this is that well, not only do we have the simplified 1982 version of create does, but we've been able to segregate the execution code as necessary by Win32.4. So a quick little summary on this. The new does was introduced by Chuck in 1982 at a formal conference. Somebody mentioned the irregularity in Bill's does, and right off the top of his head, after a moment or two thought, Chuck said, oh, well, we could put a subroutine in line, and that could locate the runtime code. And he said this verbally in about 4 sentences, and people, all of us were immediately astonished. In our head, we were doing a little bit of a compilation of what the code would look like. We saw the beauty of it, and it was immediately accepted. And all subsequent forths since that time have used that structure. There's another approach in defining words, a semicolon code. That's a separate topic, and we can discuss that at some other time. So that, as a forward-looking item, the create does and semicolon code could be used at the core of a metacompiler. Right now, they're just adjuncts, and the traditional metacompiling process actually segregates the runtime do code, do colon, do var code for ease of metacompilation. But you can design a very straightforward metacompiler just using create does and semicolon code. So that's enough for today. Appreciate your rapt attention. Are there any questions? I'll attempt to address them.
Awesome.
Excellent. Excellent.
Amazing. Wonderful. Hey, Bill, I have a question.
Yes.
Do you know if the, see, I haven't, even though I wrote Win32.4, it's gone through a major evolution after I stopped working on it. And I'm just wondering if the changes that you're talking about in Create Does occurred during my time or after that time.
Let me preface that and then try to remember to come back to that question. Changes in Forth over time. As you probably know, I'm writing a book on Win32 Forth. It's currently at 350 pages, and yeah, I hope it'll be released sometime early mid next year. In it, one of my points is that it is astounding that the architecture of Forth has been maintained all these years, clear down to the register value. So fortunately, we're all using words like IP and SP and RP, W, WP. The internal registers of Forth these days have been carried through very, very uniformly, which means that you can pick up Forth implementations these days and read them with knowledge that you developed back in the 80s and 90s and still be right up to speed. There have been additions and changes along the way. They are incremental, nothing revolutionary. The original vocabulary structure was a rigid tree structure, and then the adding only and also freed up the dictionary, the vocabulary structure. Create Does has been a benefit. I can't think offhand of any other ones that were as pervasive as those two were. But you know, the final summary is that the 60-year history of Forth has had an amazing uniformity. And to give a commercial for Win32 Forth, the development of Win32 Forth is basically static since about 2016, really more like 2010, 2012. So we have about a 10 or 12 year history on that as being a stable implementation, which is very comforting because I can do documentation now that covers a 12-year span, and we're not aiming at a moving target. Things like Polyforth changed, FigForth came along, and Leo Brody's books came along, but they are all functionally, I hesitate to use the word out of date, but they're limited because the usages have changed over time. But Win32 Forth now has been a very stable environment, and I hope it remains so. One of Andrew McEwen's concepts on doing that when he did it in 1995 was he took FPC from Tom Zimmer, and he said up till now the computer memory has been limited, execution speed has been limited, but when the PC computer got away from a 1 megabyte of RAM and exploded into megabytes and gigabytes of RAM, Andrew said to himself, he said, I want it all now, and I want it all in one system. So if there was anything he thought he might like in the system, he put it in. And there is more stuff in there than you can shake a stick at, including it's got object-oriented programming buried in it and a number of other architectural elements. So there are words in there like dupe, 2-dupe, 3-dupe, 4-dupe, 2-dupe, 2-drop, 3-drop, 4-drop. Who uses 4-drop? I don't know, but it's in there just in case you happen to need it. So anyway, hope that answers the question. The good news is that your knowledge base developed over the years is still quite useful. Well, thank you very much. I appreciate it. Onward here. We had a very good meeting today. Very lively, very interesting. Thank you so much.
Thank you, Bill. That was good.
Klaus? Klaus, do you have any questions or want to say something? You are muted.
Oh, this was just a sign for appreciation, not that I wanted to say something.
So the next participant with 2 presentations and a workshop. Oh, sorry, it's Jos. Jos, you have a question? No? Okay, your hand was up. Oh, the next participant with what is your theme? I don't have the agenda here.
Conditional compilation, if and friends.
Excellent, Klaus. Thank you
Okay,
very
so
much.
Brett Nelson is not here. Or
No, he's not
what
in the
happened?
meeting.
Ah, okay. So first of all, why did I choose this topic, or why did I bump into this as a problem? As some of you know, I'm using GeForce 0.6.2 as the basis for the microcore cross compiler and IDT. And because of the wild configurability of microcore itself, the supporting code, cross-compiler code, also has to react to the different versions of microcore that can be created, which means that I have to make a lot of use of bracket if, bracket else, bracket then. And even I have to nest them. And after a while, it turned out that the bracket if type words were buggy in GeForce 0.6.2. I don't remember what the bug actually was, but I had to roll my own. And then I looked at different implementations in different force systems, amongst others, Win32Forth, how they defined the bracket if, and I didn't like all of that because, to my feeling, they all use too much code because they solved the problem by doing string processing. Like, I mean, when they were looking for an else, they would go ahead in the source code and do string matching and matching the bracket else or bracket then code. And that meant that some string operators had to be defined before you could get your feet wet in the conditional compilation words. And on the other hand, it is clear that the dictionary is a string matching mechanism all by itself. And so I made a radical deviation from previous practice, and I did not define those kinds of string primitives. I just use the dictionary, and now I start screen sharing and I show you the code. Okay. This is not what I want, but wait a second. No. This is what we want. Okay, so this is all you need in order to do it. And the point is, and you see this in the most important part of it is this if decode. I'm not doing actual string comparison. I just go ahead. Yeah, I have to start here. When I bump into a bracket if, which I have defined here as a deferred word, and later on I have actually defined it because previously I need the bracket if decode in order to define it, and the bracket if decode needs the bracket if, so this is a forward reference. This is a circular forward reference which can be solved by a deferred word. What I'm actually doing is when I bump into the bracket if, I query the flag. If it is a true flag, I'm done. And if it is a false flag, I start with a word find and if decode. So word find just goes ahead in the source text, does a blank word, so it extracts the next word, then it looks whether this is an empty string. If it is an empty string, I fall out of this while repeat loop and I do a refill, and then I go back to blank word. And if I find a word, if the word is non-empty, I find a real text string, then I do find. And if I find it, I exit word find, and that brings me into if decode. And then I look up what I have found. Is it a bracket if? Is it a bracket not if def, if undef, bracket else, bracket then? Then, because I want to be able to use commenting to uncomment certain clauses of the if else then structures, I also have backslash and parent here, which do their thing in when I'm inside of this loop. And then because it was so easy to add once I have this whole structure set up, I also, and these are these two lines here, I also give a multi-line comment capability with a syntax that is used in many other programming languages. And you see this, the bracket star is a one-liner, so that's cheap, and so I started it in. And depending on and if I don't, if the word I have been finding here is none of the above, then I just throw it away. I'm not interested in it at all, because I'm only looking for one of these guys. And there is a special one here, which is the end of file, because I have to, the if decode requires an executable token. And when I'm at the end of the file, which means that the refill returns 0, then instead of giving you the xt that was found by the find itself, which with this exit, I just put an end of file on the stack, and the end of file itself, I mean, it's just a no-op. It's just a header that generates its own execution token, which is a unique number. And so it is, if in the if decode case, I find an end of file mark, then we have an error, because if I'm inside of this loop, I got there by the bracket if, so eventually I have to find a bracket then. And if I bump into the end of file, then, well, I just say then missing. So that's an error case here. All other XTs are just ignored. And how do I get out of this loop? The loop continues looping until the if decode returns a true flag. And so if none of these cases holds, then I have to return false, because I will have to continue, get the next word, check what it is, compare it against the ones I'm looking for, and eventually, well, let's say I find a bracket then. I have to step back a little. I wanted to be able to nest if else then structures. And to this end, I introduced the variable nest, which is initialized to 0. And if I bump into a then, the true flag that I need in order to get out of this loop is just, in this case, nest fetch 0 equals, because if the nesting level is down to, oops, we are here. If the nesting level is down to 0 when I have found then I know I'm at the end of a conditional construct. And I can continue with my normal force processing and interpretation. And if this then that I found was part of a then of a higher nesting level, I have to do an unnest anyways. And so the unnest is just nest level fetch 1 minus. And because this is not supposed to be ever negative, I do a 0 max, and that's the next actual nesting level then. So yeah, that's about all. The else clause is the same thing, basically, all minus the flag testing. It also looks for the coming words and until it finally expects the bracket then. And then the until is left and we continue. And the bracket then, if I find a single bracket then, so if I've never been at a higher level, I will eventually find the bracket then. Right now, I'm even getting doubts whether I will ever get into this situation and whether the bracket then has to, well, it has to be a deferred word, otherwise I wouldn't find it. But I don't know whether, well, usually I don't find a singular bracket then. A bracket then, if it is correctly formatted, must always be preceded by a bracket if. So perhaps at this point, in order to make the code even more correct, I would have to issue an error message saying bracket if missing. Anyways, so how does the backslash work? Well, I just postpone the usual backslash, which means skip all code until the end of the line, and I return a false because I have to keep inside the loop, because after all, I'm still trying to find a valid bracket else or bracket then. The parent is the same. That will just do what the parent usually does. I may have uncommented a bracket else clause in that in that case. And the same is true for the backslash, the multi-line comment. If that is inside of a conditional nested construct, then also I have to execute it at this point, but still continue in this loop. And yeah, that's it. That's it. Yes, your questions, please.
Can you explain colon no name? How does that work?
Colon no name. Colon no name. I think that is part of the standard. It starts a colon definition that doesn't have a name. Instead, it returns its execution token.
So colon non, this is the cleanest way to define a deferred word. So after the semicolon, there is an xt, which points to the do colon question exit, and I assign this to bracket if.
Okay. Very good talk. I learned something.
And I venture to say this is the most compact form of a conditional compile word set, the most densest form I have ever seen. And also, I mean, up to now, it worked in all the circumstances that I'm interested in. The only gotcha, I have to warn you, if you use bracket if and so on in a context that, well, of course, in the context that does not include the Force dictionary itself, you still have to then compile into this new context or this other context. You have to define the if, not if def, if undef, bracket else, bracket then. But also you have to redefine in the new context, you have to redefine your end of file and your, wait a second, there is a second word. This one. Your star backslash, or else the code would fail because these words have to be found for a properly formatted conditional compilation. More questions? Okay. So I'm back in the group. This is Bracket If and Friends Revisited. Oh yeah, that would have been a nicer title, Bracket If and Friends
Is this code somewhere available?
Pardon?
Is this code available somewhere?
Yes, in the Facebook Force 2020 group, I have made a short posting, I think, as a comment to Peter Force's last invitation that has both the pointer to the code. No, that is not true. It doesn't have a pointer to the code. It just contains a picture of the code.
Yeah.
It
So if you have to add it to Agon Fort or something because it doesn't have conditional.
Yeah, I see your point. You want the full source code. I tried to do this with pastebin, and then I gave up because pastebin is just. I mean, I didn't find a way to do this sensibly with pastebin.
Oh.
So, and then I just made a picture out of the code, and I put it at the end.
Klaus, if you want to send me the code by email, I can put it on the Force 2020 GitHub.
Good, I will do that.
Also, you can become a contributor, or I think you are in the Force 2020 GitHub.
Ach so, yeah, that may well be the case. Ach so, I could have put it there and then used a pointer to this code. Well, you know this. I have never done this, so this didn't come to my mind.
We created this GitHub account so all participants can hang your developments into the Force 2020 GitHub, and from there anyone goes to your source.
Yeah. Yeah, I will do that, Peter.
Okay.
So this was the end of the presentations, and now we come to the workshop. And the workshop is, let me see the topic.
The digital analog, no?
It doesn't say what it is about. So this time I would like to talk about connecting peripheral chips or integrating peripheral chips with microcore. And as a simple example, I picked a digital to analog converter because that is an easy thing to do. And nevertheless, you will see that this, if you do this in microcore, this looks very, very different from how you do this on microcontrollers. And so I will start screen sharing again. Okay, we don't need this. We don't need this anymore, but we need something else. Oh, where is the code? Wait a second. I have to look for it. Microcore peripherals, there we are. I don't know whether you realize this, all of you who ever looked at the microcore website. I have added another repository, which is microcore peripherals. And this will be hopefully an ongoing collection of peripheral interface code. And what we have up to now is the 64 megabit SDRAM from the Cyclone board, an ADC, the DAC I want to be talking about today, and a serial E-square PROM, namely the AT24C1024. So we concentrate on the DAC code today. And let me clear up things here. Okay. So this is now not FORCE, this is VHDL. And in order to control the DAC 121S101, this is a pretty, I mean, this is an aerospace part, but the architecture of it is one of the classical architectures that is more or less standard nowadays. There is an SPI interface to the chip, and it is a 12-bit D2A converter. And what you see here is the code you need in order to, I mean, this includes everything. This includes the SPI part, which is basically this here is the SPI interface that does the shifting. And then here we have a part that gets the thing starting, and then here we have a part that does a DAC pause, and what that is, I will come to this later. In order to do this, we need an internal variable. Oh no, what I want to say first is the end result of what I'm presenting today is that in order to set a new value into the DAC, all you have to do is DAC-rec, you see this here, and I will define it in a moment, is an internal register in microcore. And all you have to do is store a value in the DAC register, and that will then be transferred into the peripheral chip. That's all You don't have to do anything else. And because of microcore's pause mechanism, you don't even have to query a status bit whether the DAC is currently busy or not. And it may be currently busy because you are setting two values in close succession, which doesn't make a lot of sense with the DAC controller, but it may be used, it may have been used recently by a different task, and so the other task cannot use it because it is still busy. And this is handled, this situation is handled in hardware, and you don't have to query any status bit to do this. Instead, if you just try to do a duck store in a situation where the SPI control is of the previous duck store is still going on, then the system just waits, or actually, if you have a multitasking system, it puts the current task to sleep, goes to a next task, and later on comes back, and then the duck, at some point in time, the duck will not be busy, and it can be loaded with a new value. So what we have to do first is we have to define a new internal register, and I will show you how this works. So I have, there is one file in the system, which is the architecture package file. Let me not get the simulation file. That, oops, let me get the real thing, architecture package. So, okay. So this defines the architecture, how many data bits we are using, how big the memory is, and so on and so on. And here we start a section where we define internal and memory map registers. And the memory mapped registers are all at the upper end of memory. And the reason for that is that if I generate addresses in order to program the memory, then small negative numbers are just a 1 byte literal that needs to be executed in order to get the address. So with the negative numbers, I get a minimum code, and therefore the internal registers start at -1, which I have. So this is -1. I have written this down because it's easy to write down, but actually, if you have a 16-bit system, this would be address FFFF. Yes, FFFF, 4 Fs. And so the next internal register is -2, and so on. And so if we want to include the duck, I would just have to say const duck register, and this is integer. We're at 9, now it's integer 10. And then what is important, I also have to increase the minimum register. Why is this so? All the internal registers become a vector, an addressable vector in VHDL, and that is defined here. This is the type declaration in VHDL, and it defines an array that extends from max registers down to min registers of the type data bus, which means these registers are all, if you have a 32-bit architecture, then data bus is 32, and so we create a 32-bit register basically. And so max registers is this -1, and it extends down to min registers, which is -10. And so with this mechanism, all we have to do is define another address for a register and bump min registers by -1. And that's all we have to do in order to make this new internal register known to microcore. So we now have duck register. Then the second step, okay.
Can I ask a question?
Yeah, go ahead.
Why didn't you put your registers down at memory 0 and go up, and then your physical
memory? No, because
memory
at memory 0, I want, let's say, variables and stuff. So I put it at the upper end of memory.
Okay.
Because I mean, I wanted to do something useful. It has to do with the way that microcore creates literal values. If it and literal values have a variable numbers of so-called literal instructions. A literal instruction, all microcore instructions are 8 bits wide. And if the most significant bit is set, we have a literal instruction, and the remaining 7 bits are a literal value. And if you execute a literal value for the first time, then the 7 bits are taken and pushed as a sign extended value on the stack. So if the literal value is -1, I will push on the stack in a 16-bit system, essentially FFFF. And if I do positive values, that also works up until 63, and the negative values up until -64. So if I have, let's say, a value of 1 pushed on the stack, and I want, let's say, a number like 100. So this is clearly above 63. Then the first literal instruction is followed by a second literal instruction. And in that instance, it is not pushed on the stack, but instead, the literal I have pushed previously is shifted 7 positions to the left, and the new literal is appended. And with this mechanism, I can create a number of any magnitude. And if I would not use the negative numbers for the registers, then frankly, I wouldn't know what to do, what useful uses I would have for the single instruction negative numbers other than, I mean, numbers pushed on the stack, but not for addresses. And so it makes a lot of sense to put the registers to the upper end of memory. So now we know the address of the duck register on the VHDL level, but for the cross compiler, we also need it in the MyForth environment. And so what we have to do on this level is host duck register target register. Well, I will just call it duck. Why not? So on the first level, duck will return and push the address of duck register, which I have defined in VHDL on the stack. Forget about this H and T stuff. That is shorthand for host context and target context. So now we have made this new register also known to the cross compiler. And
can I ask another question?
Okay.
So instead of why do you put the address of the DAC on the stack rather than it being memory mapped and you just fetch it like a variable?
Yeah, it is
it is the address of the DAC.
Oh, okay, okay, never mind.
I mean, it is the -10 that I defined in VHDL, and here I have kind of ported the -10 into the MyForth environment.
Yeah, I get it. Sorry about that.
Okay. So then in the code section, so these are the preliminary steps to create a new internal register. Then the question is, what do we do with it? And here we come to the VHDL code for the DAC itself. A few words about this parameter list in the so-called entity declaration. So the entity declaration is the interface to the remaining code. So later on, I just have to feed parameters for these signals in order to be able to call the code that follows here. And the first parameter is the microcore bus, which gives me a collection of signals that are used in the entire microcore system. And that makes connecting something into interconnecting microcore makes it very easy, because all you have to do, you have to write down this microcore bus, which is the so-called microbus port. And I will just briefly show you what is behind this. This is the so-called type declaration, and you see the microbus port is a reset signal, a clock enabled signal. The chain thing is very special. The pause signal, a delay I can impose on the clock signal, like that is, for instance, important with the SDRAM that takes a longer time than one microcore instruction per se. And so I can use a delay system to extend a microcore cycle. A tick. Here are the sources, part of the microbus, which are all the internal registers. As you may or may not remember, the type declaration I did right there. There they are. The data sources, this is the array of the registers, and so the sources are of the type data sources. And then there is the data IO. All these words here and signals here deal with external memory and external registers. Like I have a register enabled signal, so the microcore control entity already differentiates between registers, internal registers, and makes an enable signal, creates an enable signal. It also differentiates internal block RAM memory that is inside of the FPGA, and then it also creates an enable signal for external memory that may be connected to the FPGA. And so this is basically all the signals that are in the microbus. And so this is the first thing. If you do a new entity as a peripheral interface, microbus is always the first thing you include there. Then we need the serial clock that is used by the SPI bus, which has to be generated outside of this entity, because this may be shared by many SPI type interfaces. And then we need the DAC pause signal, which is generated here, and that has to be sent back into microcore
such that the pause mechanism works correctly. I will come to this later. And then, of course, we must generate the two signals that are needed besides the S clock that are needed by the DAC, which is the DAC chip select and the DAC D-in. Well, I used the name on the peripheral chip side because there it is called D-in, whereas from the microcore point of view, it is actually a data out. And I mean, this is just a side note. Calling signals in and out is a very, very bad idea in VHDL because whether something is in or out depends on your point of view. I mean, depending on which side of the interface you are, the in signal becomes an out signal and the out signal becomes an in signal on the other side. And so this is an issue in the memory interface especially. So what is data in and what is data out? And it took me a number of years to finally find that R data and W data is a much clearer indication of what is happening. R data meaning read data, and that is clearly coming data from the memory into the core, and write data is something that comes from the core, or let's say that comes from the stack and goes into a memory. And here, I mean, I just reuse the name that the peripheral chip itself uses. So I will say some words about the code itself. So here, if we go into this, the action that happens is whenever there is a positive S clock transition, then this if condition is true, and we go into this if else if clause. If the chip is currently busy, that means if the chip is sending a data stream through the SPI protocol to the peripheral chip, we do the following. We shift the shifter, which we initialize here. We shift the shifter to the left, and then we decrement the duck counter. Oh, in order to understand the code, we have to do this section here first. And there is a function that is defined in the, oh, this is also in the architecture package. This expression is true when I do a store on the duck register address. So if I say duck store, then this expression is true. And if busy is 0 at that time, which means that the duck is not currently used by somebody else, I initialize the shifter by taking the data, which is in Norris, because this is actually what W data is. I take 12 bits and I beef it up to 16 bits because this is what the SPI bus needs for this duck. And I store this into the shifter, which is, you see the shifter is a signal here, which is an unsigned vector of 16 bits. So, and then what am I doing here? Ah, okay, I know. We set duck write to 1. Well, the reason for this is the following. The micro register write is asynchronous to the SPI clock. So I have to use an intermediate flip-flop to tell the SPI clock synchronous part to hand it over to this SPI part. So duck write is as 1, and if then S clock is 1, and if the thing is not yet busy, because as you can see here, this is not busy yet, and even if we do the duck write at 1, it is still not busy, so we fall into this else, and the duck write is 1. Now we first of all reset the duck write flip-flop, and then we set the duck counter to 16. And so in the first step, we initialized the shifter. In the second step, we initialized the bit counter of the SPI interface. And then if S clock enable is true for the next time, then busy is 1, because where do I define busy? Here. So busy is 1 when the duck counter does not equal 0. So here we have set the duck counter to 16. So busy goes to true. It is true. And so what we do is we shift the shifter 1 position to the left, and we decrement the duck counter. And then the question is, what is the value we send to the peripheral chip? Well, that is duck in is just the most significant bit of the shifter. And so this way we send out all the 16 values we have. Then if duck counter counted down to 0, busy is no longer true. And so busy is 0, so this if is not true, and the duck write is also 0, and so the SPI or the duck interface doesn't do anything else. But busy is 0, and so we could start with the next duck store cycle, which would again send the new value. So then what happens if we do a duck store while busy is still true? That means while a transfer of a different task is happening to the duck, and that is handled in the signal duck pause. If we do a write to the duck register and busy happens to be 1, then we raise duck pause, and then the pause signal will be raised, which means that the store instruction, which microcore tries to execute right now, will be sort of, well, not really interrupted, but it will be abandoned. And the address of the store instruction will be pushed in the PC, and then we start, because we then go to the pause trap, we will do either one of 2 things. If we have a single task system, then the pause trap will just execute a no-op and then return again. And so returning from the pause trap means that the PC points at the store instruction again, and we will again try to store value into the duck. And as long as the duck is still busy, this is going to continue, and we will create a pause. We will call the pause trap over and over again until finally the duck is no longer busy, in which case we will be able to shift the next value. So that is kind of the part you have to do on the interface code in order to get the mechanism going. And unfortunately, this is not all you have to do, but you have to tie both the pause signal into microcore, and you also have to tie, well, let me step back. When we define in an internal register, then in the case of the duck register, if we do a store, then it is very clear what happens. We do exactly this. We transfer a value into the shifter and we start the SPI transfer protocol. But what happens if we do a duck register fetch? And that has to be taken care of as well. And so here you see microbus sources, and you see all different kinds of registers. And so with a duck register, we would have to add an instance here. We would say microbus sources of duck register, and we assign OT0. This is a shorthand way of saying, well, we will just return 0, because, I mean, you cannot read anything out of a duck. But in order to have a clean situation, we just say, okay, if you do a duck register fetch, you will always return 0. You will also always find 0. And now I have an idea. I mean, what we could actually do at this point is not return a 0, but we could return a flag that tells us whether the duck is still busy. So in that case, we would have to say, what do we have to do? We have to, oops, second. So the busy is the duck chip select signal. So what we have to do is resize duck CS, 1, sorry, data width. And in this case, if we do a duck fetch, we would read 1 if the duck is still busy, and we would read 0 if the duck is not busy, but this is not actually what we want. What we want is exactly the opposite. If the duck register reads at 1, then we know, okay, the duck can be used, and if it is 0, then the duck cannot be used. Whatever is your favorite choice. In the VHDL code itself, I personally have the following procedure that I follow very strictly. I mean, you have on the peripheral chips, you have inverted signals, and the names usually append an N to the name of it. And if you carry this inverted signals into the VHDL code, you sometimes have to do a lot of brain twisting in order to understand of what is happening, especially if you write logic expressions. And if you have to deal with positive and negative logic, it just becomes a nightmare. So personally, I have adopted the style that internally in microcore, I will always use positive logic, and the turning into negative logic will happen at the highest level, which is in this file, which is called the FPGA.vhdl, meaning, well, this is the wrapper of the entire FPGA, and these are the pins of the FPGA that are being used. And for the duck,
as we are talking about the duck, so we have to add something to this. DAC, we would have to say duck CSN, because this is what the peripheral chip needs. This is an out signal of standard logic, and we have a duck. How did I call this? DN. This is not inverted. This is also a standard logic system. Later on, these signals have to be assigned an actual pin. I mean, I have made comments here in the VHDL code on which pins these signals are. I mean, as a designer, you will know where you put the peripheral chip, so you have to stick the proper numbers in it. And then we have to instantiate the let's have a break. Are there any questions up to this point?
Yes. So what happens exactly to the microcore if multiple pause signals are active and multiple tasks are?
No, there can always only be one pause signal active, because the pause signal usually is the result of a fetch or a store to an internal register. And you are addressing a certain register, and so it can only be one single source.
Yeah.
And this is something, this is something we have to do. But the first thing we have to do, I mean, on this level, we only have defined how the entity looks like, but now we have to integrate this entity in the complete design. Yeah. And so the way we do...
Sorry, but I was wondering what the pause signal is active, then the CPU gets either paused or switched to a different task. And what happens then?
Pausing it means it switches. I mean, if it is a single task system, then it just does a no-op in the trap. And if it is a multitask system, I do a multitasking pause.
Yeah.
And let another task run.
But the pause signal is only active at the hardware level for this very brief moment.
Yes, only for this very brief store event.
Yeah, okay.
So we have to stick. I will not do everything that is needed. I will make here now a quick simplification. So I first get the code. We have to stick it into FPGA because on the highest level, this is where we want to put the interface to the duck. And at the very end of the file here, we have the different peripherals. So we have DSD RAM. Okay, let's put the duck here. So this is, and now we have to do some re-editing. Now this is, this now what you see is VHDL. It is obsessed with tiny little differences depending on what you do. We have to erase this. Then we have to throw, all of this away. And instead we now do a, let's say how would we call this? An association of the signals. So this is just microcore bus. This is, mistyping.
This is just SCLKEN. Well, to be as honest, I have not defined SCLKEN yet. That has to be done as well. Of course, we have to generate the SPI clock. So we do duck pause. We do duck CS. We associate it with duck DN. And then we do have to invert the duck CS, because this is what is needed by the interface. And so we say not duck CS. And that's about it. And now we still have to take care of the pause. And in order to do this, I will just search for where I do all these pauses. Nah. Okay. So here we have all the pauses. So what we would have to do is duck pause. So this connects our new duck pause to the pause mechanism of microcore. And that is almost everything that has to be done. Save the SPI clock. I mean, that is more or less trivial. I will not go into this now. I think otherwise this is too much. And what you can see from my presentation now is that interfacing an SPI type peripheral to microcore is a very different story to programming an SPI interface on a microcontroller level, where you have to do, where you basically just have the serial protocol to your disposal, but you have to do a lot of software work to send the proper information across the line, which if you do this, I mean, basically what your SPI interface in your microcontroller does is basically, this is basically this code that an SPI interface is performing. Plus, in the microcontroller world, you have also configuration bits which say how many bits have to be shifted, whether it is positive or negative logic, and whether it is acting on the positive or negative SPI clock edge. But you know this. I mean, if you program the interface for the duck, for a specific duck, which I did, this is not a general purpose one, this is for this very duck, which is very representative for, I would say, the most DSAs nowadays. You know what you need, and you don't have to configure it, but you just write the code in such a way that the code does exactly what the peripheral chip needs.